right, we're going to start the second section of these talks that I called a potpourri of crystal chemistry. And what they are a general discussion of organic crystals and their chemistry from the standpoint of a general scientific audience. These are not intended to be highly technical, but at the end of each section I'm giving the references to articles we've written about these systems if some of you would like to read further about them. I'd also like to mention again that these talks are biased towards work that I have had experience with and also towards work that we have done that has some interesting visual consequences that we could record for you to look at. Okay, now I'm going to move over to the slides here. In this particular section, I'm going to be talking about crystal growth and crystal morphology. We will also see a little bit of a couple of phase transformations, which is what the topic of the first hour was about. It's kind of hard to sort these out completely, so we'll review a couple of the phase transformation ideas. But I'm going to concentrate mainly on crystals themselves and not necessarily their reactivity this time. Ah, yes, thank you. Now I'm going to back up. All right, now part of this slide may be off your tape, but what it says is a tenet which I'd like you to hold for the next hour with me while I go through this talk, and that is that the crystal growth process is fundamentally governed by scientific principles. It's not just an art, but soft background music helps, right? And what we'd like to do is to think a little bit about what are some of the scientific principles, what can we learn about molecules and about chemistry from looking at crystals, and to bring crystal growth out of the dark ages where it was only an art. And for most chemists it still is only an art. But these are molecules and this is chemistry, and so what can we learn about it from crystals? And this is what I call a hover model. This was introduced to me at a meeting I went to in Poland. And this is a model of intermolecular interactions. And that's really what we're talking about. We're talking about weak directional interactions where there's a very shallow potential curve so that the directionality is not very precise. It doesn't take very much energy to distort one molecule encountering another molecule. The distance between these molecules doesn't take much energy to change that. But we nevertheless do have some directionality, and we can use that idea once we understand it. That hummingbird is not going to hover over here. It's going to find one of these flowers and direct itself somewhere around the flower. And that's basically what molecules do when they encounter one another. There are certain directional interactions that we need to learn about, and when we do, we can use them. Now this slide is in honor of the St. Paul Winter Carnival, which starts today. And these are snow crystals, which we're all very familiar with. But what I'm showing you here are snow crystals of all different shapes. Even looks like some of them have different symmetry. And what is the difference between these crystals? They all have the same internal structure. So any physical or chemical measurement you made on them would be identical. You couldn't tell that they're different compounds. They are not different compounds. Crystallographically, they're identical. What's different is that the environment around the face of these crystals was different when they grew. And all that's changing is the rate of growth of the crystal faces, the relative rates of growth of the crystal faces. And they're changing here by humidity conditions or temperature or perhaps the wind flow or whatever. And that's what's making one crystal face grow fast on this crystal but not grow at all perhaps on this crystal. And so what we say is that the differences between these crystals are differences in morphology, in shape, but the internal structures are identical. Now this is a tricky business because a lot of what we do with crystal chemistry is to use a microscope and look at crystals. And often when we see a change in crystal shape, we attribute it to a change in chemistry. And often that's the case, but not always. And this is something you need to really be attentive to if you're interested in polymorphs and forming new crystals. The possibility that that your reagent crystals might simply grow with different morphologies under the conditions that you're using is something you need to always keep in mind. Now what I'm going to show you are a series of paranitroaniline crystals. We've been interested in this molecule for a long time. The molecule has an asymmetric pi electron system, which is easily polarizable, and thus this molecule is in principle usable for some interesting electro-optic effects. The problem is the molecule, when it crystallizes, so here's a molecule that has a net dipole moment. When it crystallizes about an inversion center like this. And so that the dipole moments cancel, and all of the interesting electro-optic effects also cancel. And so paranitroaniline is one of these gems that if you could get your hands on it and put it in a space group that had no center of symmetry, you might have a really interesting electro-optic material. And so I thought when we started this work, I said, well, look, we know about growing polymorphs. If you take organic compounds and just work hard on them, eventually you'll get a polymorph. Almost all organic compounds form polymorphs. And to top it off, I had a student whose name was Crystal. So I knew this experiment was going to work, and what I had her do was to try all different solvents and all different reaction conditions to try and make polymorphs of paranitroaniline. Any polymorph. I didn't care if it was centric or not to start with. And so she started growing paranitroaniline crystals, and these crystals I'm going to show you are all about 4 or 5 millimeters long. These are quite large crystals, and some of them can be grown gigantic if you want to. Paranitroaniline grows very easily. And the crystals I'm going to show you come out of different solvents. Here are 2 other crystal forms of paranitroaniline. Here's another one. Here's form, what we call form C. It's still just plain paranitroaniline. And what Crystal found was that there were these 6 habits that came out of different solvents. Sometimes you got mixtures, usually you didn't. And it was a very long, tedious project, but she had to convince herself every time she got a new shaped crystal that it was not a polymorph, or find out whether it was or not. Or is it just another morphology? And it turned out that all of these were simply different morphologies of plain old paranitroaniline. We never got a polymorph under any of these conditions, and Crystal went to medical school. And this is really unusual because it's more often or not the case that we can get polymorphs of organic compounds simply by changing conditions and growing, doing 10 or 15 recrystallizations. I wish I had some idea about why particular molecules don't like to grow polymorphs, because there are some that are really resistant. And there are others, like I showed you earlier this morning, where you get 14 polymorphs. But looking at the structure of the molecule, I have no idea at all whether it's going to be a potential polymorphic candidate or not. All right, so this is a very typical kind of practical situation that we run into in the laboratory. Now, what I said we'd like to do with paranitroaniline is to take the molecules which like to pack this way and put them all in the same direction. Then we would have a net dipole moment, macroscopic dipole moment, and we would call this arrangement a polar crystal. And so these wood ducks here are arranged so that the vertical direction is polar. All their heads are up. The horizontal direction is not polar. And the axis coming in and out of the screen is also not polar. They're essentially a mirror plane through those wood ducks. Now these rabbits, it's polar in the vertical, not polar in the horizontal, but it's polar in the direction in and out of the slide, right? Either of these arrangements could have nonlinear optical effects. What we want is any polar direction in the crystal. That's all that is necessary. All right. Now that's not sufficient. You need other properties of your molecule and crystal. But our research goals were to try and learn how to take molecules of any kind and put them into polar arrangements. And when you do that, frequently you will see crystals that have polar shapes. You see, there's no center of symmetry in this shape. So what we're often looking for in our crystallizations are crystals that look like arrowheads or have shapes like this. And when you see it, it's really quite spectacular. And you know that you have polar morphology when you see a crystal like this. All right? And so I'm just going to back up 1 second here. All right, so we've spent a lot of time thinking about how you can get molecules to do this. And from the literature and just from discussion among other people who grow crystals, there was a little bit of lore about crystal growth. And that is that if you take molecules that are acentric, that they should bias the final three-dimensional structure to be acentric. And we took this idea one step further and we said, if the molecule is acentric, and if its associated sets of molecules, say hydrogen-bonded sets, were also eccentric, that hydrogen-bonded set might nucleate crystal growth, and that might even give us a little more bias towards a final acentric crystal. It's not necessary, because those chains can go this way, but we're saying there might be a bias. So this was kind of the lore. So when we started our work, this was what we knew about making polar crystals. We would start with meta-substituted compounds, and if you look in the literature, they frequently form acentric crystals. Just that simple property of the molecule. Now let's put groups on that molecule that allow us to form acentric chains of molecules, and then if we're lucky, acentric planes. And all of those will give you a better chance of getting an acentric crystal. However, we're stuck with a little prayer and a hope that the final crystal will be acentric, because there's nothing controlling it or forcing it to be that way. You can take acentric planes and have them go in opposite directions and introduce a center of symmetry into the final product. So we thought we might like to have a little more control over this process. This is fun, but that really is art. So one of our approaches has been to say, if paranitroaniline wants so badly to grow in one particular crystal type, and we can't force it out of that crystal form, let's introduce another molecule into the crystal and provide a different environment for it. And if we have a choice of many different neighboring molecules that we could give it, then we have a wide variety of choices about trying to put paranitroaniline into a new environment. Okay, so our approach was to look at host and guest molecules that would form strong hydrogen bonds to one another. And the idea is, if you take a molecule like triphenylphosphine oxide, which has a very strong proton acceptor on it, and put it in the presence of a molecule where none of the functional groups on that molecule are better acceptors than this one, that in solution, that oxygen will find that hydrogen. So they'll pair up in solution and a co-crystal will form. And in fact, this has worked in many, many, many systems. I mean, probably we're close to hundreds where this idea has worked, just that simple idea. I'm showing on the right an ORTEP of the crystal structure, and on the left just a schematic. So here's a way, by introducing a guest molecule into a system, we can put our original molecule into a new environment. And by changing the groups on this guest, we can change the environment almost with infinite versatility. And what I'm showing you here is there is an added bonus to using triphenylphosphine oxide. This is one of those things we weren't looking for, and we almost missed this effect, in fact. But I'm going to show you several different crystals here. These two crystals are just plain triphenylphosphine oxide. It grows in 3 polymorphic forms, and I'm just showing you one of them here. And the more stable form are great big huge crystals. So triphenylphosphine oxide really likes to grow nice big crystals. If you take the triphenylphosphine oxide and grow crystals of other organic molecules where the organic molecules grow crystals that look like this, the co-crystals look like this. And these are like ice cubes. So the good crystal growing properties of triphenylphosphine oxide are incorporated into and help the other molecule grow nice crystals. All right, so this was kind of a bonus, and this happens so frequently it was really quite remarkable. This particular example is phenol, which is a liquid, and there's the phenol co-crystal. Now the other nice benefit of using something like triphenylphosphine oxide is that it's a big molecule. And if you don't have very much material and you're trying to crystallize it, you can increase its molecular weight by incorporating triphenylphosphine oxide in. And you might even have several phenol or amine or amide groups, and you might be able to bring in 2, 3, or 4 triphenylphosphine oxides and have a lot more bulk to work with, and also have the chances of making better crystals from the material that you're working with. So this trick has really worked nicely in a lot of cases. Now what I'm going to show you are some other co-crystals, and one of the things we're going to see here are that the co-crystals often look bigger and sometimes of higher quality than the starting materials. And in our hands, we see that to be the case a lot of the time. And I don't have any good rationale for it, and it doesn't always happen. But it happens enough. And if you're a crystal grower, you will take any small advantage you can get. And so in my mind, if you're having trouble growing a crystal of your compound, think about a co-crystal, even if it's not with triphenylphosphine oxide. And so I'm going to show you several examples of this phenomenon here. I've had to write down the names of the compounds so I wouldn't get them mixed up. These are crystals grown by Gil Frankenbach, and what she's showing is one of the reagents and what its crystal form looks like by itself. The other reagent and what it looks like in its homomeric crystal form, and then the co-crystal of the pair. And this one is paranitropyridine and oxide and hydroquinone, and then the one-to-one hydrogen-bonded co-crystal. And the crystals are grown with the same degree of care. So it's not like she spent weeks working on growing big crystals of this, but only 5 minutes there. It's the same sort of system, the same amount of time, but she just gets enormous big crystals of this co-crystal pair. Now, we talked this morning about grinding materials together and getting co-crystals by grinding. All of the cases I'm showing you, you can form that same co-crystal phase by grinding the two materials together. But by grinding materials together, that is not a good way to get nice single crystals. You end up with powders, and you sometimes would like to have a nice single crystal, either for crystallography or for actually making optical or electro-optic measurements on it. All right, this crystal, these are 3,5-dinitrobenzoic acid. Those crystals grow really well, and I suggest that as a guest molecule if you ever want a guest molecule to promote good crystal growth. This one is a general common system. It has a very acidic proton on it and is useful in many cases where triphenylphosphine oxide doesn't work. On the right is para-aminobenzoic acid, and this is their co-crystal. Now, you also notice you're seeing color develop, and that's because we're using aromatic systems that have donor-acceptor characteristics to them. And when they come into the crystal together, you're getting charge transfer interactions. But we really think it's the hydrogen bonding interactions that are driving these changes. Here on the left is para-aminobenzoic acid, and on the right is 4-chloro-3,5-dinitrobenzoic acid, and there's their co-crystal. And I also talked in the first part of this series about the solid-state reaction that occurs in this co-crystal, where you get the nucleophilic aromatic substitution reaction. And now this one is para-aminobenzoic acid again, 3,5-dinitrobenzoic acid again, the nice crystals, and here's their co-crystal pair, and look at the shape. All right, this is one that is polar. It's a polar crystal. It has a nice second harmonic generation. It's a nonlinear optical material. And so we finally found a way here to take molecules that are centric and put them into an acentric arrangement, and to get a fairly significant second harmonic intensity here. And if you were to look at the hydrogen bond patterns of the molecules and how they pack in this crystal, you could have predicted that you would get acentric two-dimensional sheets. We couldn't have predicted that third dimension still. But the way the hydrogen bonds should match up, you should get an acentric sheet, and we do, and it biases the final structure, in this case, to be acentric. All right, now I'm going to move on to some crystals. I'd like to point out that these are black and white slides. These are not colored, but the crystals are transparent. All right, some of them are pale yellow, I believe, but we're using black and white here. Also, again, we don't have scales, but most of the crystals we're going to be looking at are in the millimeter range. And one of the reasons we have so many crystals that are about 1 millimeter long is that that's about the size, 1 millimeter or a little less, that you need for X-ray crystallography. So we don't always try and grow huge crystals. We try and grow crystals that are about 1 millimeter long or a little less. And if they're too big, you got to cut them. And sometimes that's a problem. It introduces defects and things. All right, these crystals are ethyl isonicotinate co-crystallized with 3,4-dinitrobenzoic acid. These crystals are grown by John McDonald. And part of what I'm going to show you in the next series of slides are how to tell when you have a high-quality crystal. And what you're looking for are sharp edges, well-defined faces, and transparency, which you see here. The problem with this bundle is that there's a lot of disorder in here. It's as if there were a little impurity, and then all these crystals grew out from the center. If you're lucky, you could take a razor blade and cut a piece off, and that would be good enough for crystal structure. But that would only be true if, when you cut it there, you find a fracture plane, which I'll talk about later. Otherwise, when you cut it, sometimes the crystal crumbles or fractures in ways that you don't want it to. So John has grown this crystal this is out of acetonitrile, and under different conditions, still out of acetonitrile. Probably what he did was make it more dilute and grow the crystals more slowly. And what they look like are this. Now these are really high-quality crystals. You can just tell they sparkle. The faces are reflective. The edges are just as sharp as razor blades. This particular one, I think, is about 3 millimeters across, so it's even a big crystal. Often the smaller the crystal, the higher the quality, because as the crystal grows bigger and bigger, it has more chance to introduce defects. It's not very often we see crystals that big that are that high quality, but that's what you're looking for when you're looking for a high quality crystal. Now, if your crystal doesn't have these nice sharp edges and reflective faces and all of that, it doesn't mean that it's not useful for crystallography. But what it probably means is that the diffraction spots that you get will be somewhat broader, because you have sort of a mosaic spread in there, that you won't have as many high angle reflections, so you won't have as much data, and so your R factor, your final structure solution measure of quality, will be poorer. So you really want to be spending a little effort to get a high quality crystal before you go to all the trouble and expense of trying to solve a crystal structure. It's really worth the trouble. But you can solve crystal structures on some pretty crummy crystals if you really have to. Now this crystal is unusual. It's tetragonal. We rarely see symmetry higher than twofold symmetry in organic systems. Organic molecules have such low symmetry. To see 3-, 4-, or 6-fold symmetry is very unusual, and when you do, you should make note of it. It just doesn't happen very often. And this crystal is like a little truncated pyramid coming out at you. So here's the top face, and then the side faces are here, and they're also transparent. It's just that in the lighting you're seeing they look opaque. But this is transparent from every direction. It's a beautiful large tetragonal crystal, and this one is a co-crystal of imidazole with binaphthol, 1,1' binaphthol. And there is nothing that suggests 4-fold symmetry about either of those molecules or the pair. So I have no idea why this grew in a tetragonal crystal. The other thing I'd like to point out, we'll see this several times today, crystals that have 3-, 4-, or 6-fold symmetry have a special property about them. 3-, 4-, and 6-fold rotation axes are called optic axes. They're special optical, unique optic axes. And if you have a real 4-fold, you might have a crystal that looks like it's 4-fold, but it might not be a real 4-fold symmetry axis. If you have a real 4-fold symmetry axis coming out at you, then the optical properties in any direction of this face will be isotropic. And what that means is that if you put the crystal under crossed polarizers, when you rotate the crystal, you will not see any extinctions. It'll be clear for the entire rotation. Whereas for a 2-fold symmetric or less crystal, whenever you rotate it, the crystal goes blank and then goes bright again. And it has to do with the fact that the refractive indices are anisotropic in a crystal. But in a crystal with a unique optic axis, the refractive indices are identical in all directions in that direction of the crystal. So it's a way to tell if you have a real 4-fold axis there. All right, now these crystals, the 2 on the outside are one polymorph, and the 2 on the inside are another polymorph. And this is the first crystal system where we've been able to get 3 different molecules into the crystal. We've been thinking of ways to make triad crystals, and John finally did it. It took a lot of thought, though. It's not easy to think about how to do this. And what this actually is a small molecule crystal model of the catalytic triad of the serine proteases. And so what we have here is an imidazolium ion bonded to a picrate and also bonded to a beta-ene molecule. And the stoichiometric ratio is 2 to 2 to 1, which really isn't critical for our purposes here. But we had no idea that this combination of molecules would form big, high-quality crystals. And apparently these grew very easily. What solvent did you grow these out of, John? Okay, so it's out of an organic solvents. And these grow very large. And these blocks here were evident. Actually, it was Professor Britton, I believe, who noticed in the beaker that there were different crystal shapes. And we've solved the crystal structures on both of these. The crystal packing patterns are very different, but the hydrogen bond patterns are very similar, which is something that we're interested in here. And John has brought in an actual sample, I believe, of this polymorph. Or is it the other one? It's the middle. It's a sample of this one, which I'd like to show you. And for those of you who think organic crystals can't grow large, they can. We don't know why this system grows large crystals. We don't know what it is about the relationship between the molecules and the packing pattern. But when it happens, we take note. And we are very interested in keeping track of crystals that grow very large, just to find out if there's anything common about the structures, because it would help us enormously to be able to pick molecules that we know will grow good large crystals if we work at it. And we don't know how to do that yet. We just simply don't know how to do that. Maybe we can pass that. All right, now this crystal, this one's about 6 millimeters across. And this would not be a good crystal for crystallography because it's, well, first of all, it's too big. But it's too anisotropic. It's very, very thin. But it's a very high quality crystal. The edges are sharp. It's completely transparent. There are no defects in it. But for crystallography, you want a crystal that's nearly equidimensional, because X-rays are absorbed by crystals. And if you have one dimension that's enormous, it'll absorb a lot of the intensity in that direction. And then the relative intensities of your diffraction spots will be all mixed up, and you have to make corrections for it. So high quality crystals like this would be useful for making optical measurements on, or making electrical measurements. You can even put leads. You could glue leads onto the faces of that crystal. These crystals would also be useful for following phase transformations and taking video pictures. They'd be useful for doing epitaxy, so you might want to grow a second kind of crystal on top of it. So there are a lot of reasons you might want a huge, big single crystal face for other experiments, but not for crystallography. And this one, by the way, is 4-phenylpyridine co-crystallized with benzoic acid. All right, now this crystal looks sort of crummy, but it wasn't to start with. It was a very large crystal. It was much too large for crystallography, so it had to be cut. And crystal cutting is really kind of fun. I suggest you do it without having had very many cups of coffee, because you take a razor blade, and you want to take a brand new razor blade. Take a little piece of Kim wipes and wipe off the oil, because when razor blades are made, they have oil on them. So dry it off, dry the oil off, and then under a microscope, you take the razor blade to your crystal, and you just touch it. And if you can find a fracture plane just simply by touching it, your crystal will fall apart and you'll have beautiful faces. And if you don't find a fracture plane, when you touch it to the crystal, nothing will happen, and you'll push a little harder and little pieces will start flying off, and you'll push a little harder and you'll have all these horrible edges and it'll just crack to pieces. Okay? So what John did, he really had to cut this crystal down on all the faces because it was so big. And I'm going to show you the crystal structure here. He found that one face formed nice fracture planes, which means all he had to do is touch the razor blade to the crystal and it fell apart. And that's true of this edge here. But the other edges he sort of had to saw on. And they didn't come out as nicely, but fortunately it was still a good enough crystal after that activity to get a crystal structure. And this structure is imidazolium succinate, I believe. All right, I'll show you at the top first a layer of the imidazole and succinate molecules alternating along a line here. And if you look at the crystal structure in another direction, 90 degrees to that, you see that these sheets of hydrogen bonded molecules are lined up just like sheets of graphite. And so there is a natural fracture plane along there. And so the crystals will cut very easily in that direction. But if you try and cut in any other direction here, you're cutting across very strongly hydrogen bonded units. And it will take a lot of energy to cut them, and there won't be any particular direction where a cut can be made easily. So you're going to have to kind of saw away at your crystal, and you'll get sort of ugly edges. But this is typical of all the crystals I've showed you. There may or may not be a good fracture plane, but there will always be directions where you can't cut it very well. If you really want to be cutting crystals under a microscope, there are some tricks. And one is, if you just put the crystal on a microscope slide and cut it, chances are that both halves will fly away. And if you have a nice clean surface, you can take a magnifying glass and spend the morning looking for the pieces. If they're on the floor, you're in a little trouble. So one thing you can do is to just simply put a little new-gel or something over your crystal when you cut it. It won't hurt the crystal, it won't hurt the diffraction pattern, and then when you cut the pieces, they won't fly away from you. And the other thing that sometimes happens is the crystal will stick to the razor blade. So you go cut the crystal, and then you pick the razor blade up, and because of static electricity or because you didn't get all the oil off, the crystal pieces are stuck on your razor blade. And so then you take a little pointer and you go along, you chase these crystals up and down the edge of the razor blade, trying to get them to come off. So these are little practical problems. All right, now what I'm going to show you are a series of polymorphs of a very simple molecular system with very complex crystal chemistry. When you're talking about solid-state chemistry, you're talking about the chemistry of intermolecular interactions and molecular packing properties. And simple molecules don't necessarily have simple crystal structures and packing properties. This molecule is anthranilic acid. It's orthoamino benzoic acid. And it's been known in the literature for many, many years. It's been known that there were a couple of polymorphs. And we started several years ago trying to sort out how many polymorphs are there. Can you tell which one is which by the shape? And the other interesting thing here is that several of these polymorphs interconvert under different conditions. Even more interestingly, this first polymorph here, which was grown by slow evaporation from methanol, contains half of the molecules are neutral and half of the molecules are zwitterionic in the same crystal. And if you think about the process of growing of molecules going from solution into the solid state, think about some situation under which proton transfer is favored, and you'd get zwitterions. But it would surely have to be a very different set of conditions where the proton transfer is not favored. And we have found that there are situations where molecules are zwitterionic in solution, but they end up neutral in the solid state and vice versa. But this is only one of two situations I know where you get the zwitterion and the neutral molecule in the same crystal. It is really difficult to imagine scientifically how such a thing could happen, but indeed it has. All right, and these are light brown. Is that right? This is work Bill Ojala did. They always have a brownish tinge to them, and this brownish color we don't really think is an impurity, because if you convert it to the other polymorphs, they don't have the brownish tinge. It seems to be a property of this crystal form. This is the second polymorph, and all the molecules in here are neutral. There's no zwitterion. And you get these crystals by crystallizing a methanol solution hot and cooling it fast. So these are kinetically favored crystals. They're not the stable form. The first form was the kind you get by slow evaporation, where you're more likely to get the thermodynamically stable form. So we think these are kinetically favored. And these crystals, upon heating or sitting on the bench top, will start to transform. Those of you who were here this morning have already picked this out, haven't you? That there's a crystal reaction taking place. It's actually a polymorphic transformation, and I'll show you this in more detail in a minute. So 2 is going back to polymorphic form 1. These are metastable crystals, and they're going back to the more stable form in the solid state. These are polymorph 3. These are much more difficult to get. They're the least stable crystal form. You can get them by sublimation. You can get them by melting and cooling. Or you can also get them by very fast crystallization out of methanol. And you'll have competition with the formation of 2 under those conditions. But these crystals can also be formed, apparently, by heating the first form. So the second form at room temperature goes to the first form, and the first form on heating goes to this form. And we're trying to work out these transformations to make sure we understand them and see if there's any rationale for the mechanisms of those transformations. And now what I'm going to show you are a series of slides where polymorph 2 is undergoing a phase change to polymorph 1, which will show up as the black. Now actually these crystals aren't black at all, they're white, they're opaque. But we're using transmitted light, so it shows up here as if it were black. But it's really opaque white, like your tabletops here. And one thing to notice here is that some of the crystals are completely transformed. Others have started a transformation. Here's a little tiny corner here. And others seem to be apparently not even beginning to transform. And again, this often happens with crystals, that the initiation temperature or time differs enormously from one crystal to another. And these pictures are taken a week apart, and the crystals are at room temperature in the open air. And so now we have a little bit more reaction here, a little bit more of the crystal phase is growing in, the product phase, and here quite a bit more. But notice this one still hasn't changed at all. And then finally, was this another week later? They've all seemed to go. Okay, so this is a very typical kind of a phase change. Trying to figure out what the product is and whether there are any other intermediates in the process when you have so many polymorphs is not straightforward. And remember again, this is an extremely simple molecule. So there's some very interesting chemistry for molecules which solution chemists have long ago thought everything was known about them, and they aren't particularly interesting anymore. Okay, I'm going to show you a couple of slides here on another phase transformation, and this involves taking just plain crystals of just plain binaphthyl. And what I'm going to do is start with a racemate, and I'm going to sublime the racemate and see what kind of crystals we get. And if you recall, binaphthyl has 2 different conformers that are enantiomeric. And the interconversion between them costs about 20 or 25 kcals per mole. So that in solution, you actually have a few hours where you can have an enantiomeric solution that has optical activity before it racemizes. All right. But in the solid state, the most stable crystal form of this compound is a racemic form. So if you have both of these in solution and you grow crystals, you'll get these lovely diamond-shaped crystals of racemate. And what I have shown here is I had originally an enormous diamond-shaped crystal that filled this whole slide of the racemate. And that's what this is. This is the racemate here. And as we heat the racemate crystal up, it vaporizes and then recrystallizes on the slide to give these pretty little rhombohedra. And these have spontaneously resolved the binaphthyl. The crystals are right and left-handed. And we call this conglomerate formation, when you have right and left-handed crystals independently. And here's another little one right here. The crystals, interestingly, are tetragonal. They have that same property that John's tetragonal crystal had. They have 4-fold symmetry in them. So here's a very unusual case where you can do a spontaneous resolution on conformationally interconverting enantiomers and completely stabilize that enantiomer in that form. And now we're going to see something which is just the converse of this. And this system is one which Professor Grant in the College of Pharmacy pointed out to me, in which he has ephedrine enantiomers. I even can't read. I guess it's plus. The plus enantiomer he has in a Petri dish on one side of the Petri dish. And all of these crystals are white. He's colored them in just for visual effect here. All right, we're not getting any color change. So the plus ephedrine, this is just a powder, ground up powder in a Petri dish. And over here is the minus ephedrine, also ground up and just sitting there. And you cover the Petri dish, and after a period of time you have crystals in the middle, and that's the racemate. So these are vaporizing and coming out as a racemate. It's doing just the opposite of what the binapithol did. So these are effects that are quite common among organic molecules, and you just got to keep your eyes open for them. You might be growing crystals in the lab and letting them sit around for a while, and from one day to the next they might be changing in unexpected ways. You rerun your IR or take an optical activity measurement and it's changed, and it just doesn't make any sense to you because you know that solids don't change, right? Okay, now I'm going to show you a little different effect here. This is a big single crystal of tribenzoyl methane. And we were very interested in this crystal structure, and the crystal quality is quite good. The crystals grow too long, and every time we tried to cut them, they would shatter like into a bundle of hairs. So we really couldn't cut them. And what we tried to do was to mount this crystal and just put the tip of it in the X-ray beam to get the crystal structure. Now if we look at the tip of that crystal, it is hexagonal. You have to sort of squint and use your imagination. But it is hexagonal, and we have solid state NMR and now crystallographic results that tell us that this crystal has a real threefold symmetry axis down that direction of the crystal. And that was important to us. It turns out the molecule sits on the threefold axis, which tells us that all three carbonyl groups are symmetrically equivalent in the crystal. They're identical, even though it wouldn't necessarily be the case. They could have crystallized in a general position, and each had a different chemical shift, for instance. But they have real symmetry there. But the problem is, when you put this crystal in the X-ray beam, it does this. This is not a phase change, and it's not a polymorphic rearrangement, it's not a desolvation, it's not a hydration. This is exactly the same compound as we had before. And we don't know why it does it, and we don't know how X-rays can cause this to happen, but it mechanically just shatters to pieces. And there's no phase change. Every chemical and physical property you'd measure on it would be identical. The only thing that's different is that it is shattered into these little pieces. And interestingly, many compounds in the tri-keto series have this property. Many of their crystal structures have this property, which we also don't understand. Okay, I'm going to show you now what I call a designed crystal system, where we think we've learned a little bit about hydrogen bonds, we think we've learned a little bit about growing crystals, and so ultimately what we'd like to do is to be able to look at a molecule and predict something about its crystal packing pattern. That would be the long-range goal, and so here's one of our attempts at doing that. We're going to take cyclohexane dione, which is an enol form in the solid state, and that's known simply from infrared studies or other spectroscopic studies. And over here we have one OH group, and that OH group could point up or point down and still be in a planar arrangement. And so when hydrogen bonds form here, we have 4 stereoelectronic possibilities for hooking these molecules together. You can talk about stereochemistry about intermolecular bonds, and that's what I'm doing here. So if the hydrogen is up, it could hydrogen bond to the top or the bottom lone pair of electrons on the oxygen. And then you could go through all the other 4 combinations there. And what we're going to do is sketch out what those patterns would look like and see what the consequences are, because we're going to get very different molecular arrangements, and they're going to imply very different chemical and physical properties for the sets of molecules. So first let's look at the syn hydrogen bond pattern. It looks like I'm putting 2 molecules together like this. In fact, this hydrogen here is sterically interacting with that hydrogen. And what happens instead of forming a dimer is it just slips a little bit, and it forms a helical chain, which in projection looks like that dimer. And this dimidone crystallizes in this pattern, and dimidone is the compound that has 2 methyl groups there. So that pattern is known to exist. This pattern here is the anti-anti form, and we formed that exact pattern by crystallizing that molecule out of THF. And the crystals we get don't look like that. I got them mixed up. These are the crystals look like that, okay? And that's just for reference. We'll come back to the other crystals in a minute. Now, interestingly, if you take the sin-anti or anti-sin combinations and draw a picture using default bond lengths and angles, you can draw a picture where the 6 molecules go around in a circle and tie back on one another. And this is kind of a challenging arrangement because this looks a little bit like a macrocyclic, perhaps a crown ether. Here's 6 oxygens pointing onto the inside. And so it's kind of challenging to think, is it possible to make that structure, and could we template it, or is there any situation where we could force the molecules to do this? And so we made the CPK models here, the space-filling models. Here's the hydrogen bond, here's the cyclohexane dione, and these are the 6 molecules in a ring. And if you're playing with these CPK models on your desk and you make that ring, you have to reach over and pick up a benzene molecule and put it in there. It just fits. The symmetry, the topology, the size is the same. And if you do that, the exterior is now hydrophobic. So perhaps in benzene, which is a hydrophobic solvent, we would template it and promote the association of these molecules into that pattern. And so if we take cyclohexane dione right out of the bottle and recrystallize it, the crystals look like this. And they're reflecting the hexagonal symmetry that I just pointed out a minute ago to that ring. And we've characterized this in many different ways, including solid-state NMR and X-ray crystallography, and the pattern is exactly what I sketched out for you a minute ago. I don't think I'm showing, no, I don't have the pattern here to show you. What I am going to show you, though, since this is a talk about crystals rather than crystallography, is that that crystal is rhombohedral. Rhombohedral crystals can have trigonal and hexagonal symmetry to them. And the morphology I showed you a minute ago highlighted, it looked like a 6-fold axis. It's actually 3-fold symmetry. It highlighted that particular symmetry. But it turns out that it's a rhombohedral symmetry, and there are crystals that have this morphology. And they're absolutely clear. You can't tell, it looks black here, but they're absolutely transparent. And these little rhombohedral crystals are simply a different morphology. They're not a new polymorph. They're another morphology. But when you look at them, you can't quite see that nice 3- or 6-fold symmetry as well. So we were actually really lucky to get that other morphology first to give us an indication of what was going on. This is a crystal of the same host molecule, 1,3-cyclohexane dione, where we filled the holes with thiophene instead of benzene. And you can only fill half the holes, no, a third of the holes with thiophene. If you have any more thiophene in there than that, what happens is that the crystal doesn't form a solvated crystal at all. It goes back to that linear chain that has no solvent in it. So pure thiophene gives that linear chain form. But benzene plus a little thiophene will give crystals with this very unusual morphology that have thiophene in some of the crystal holes. But the morphology is quite characteristic and quite different. In fact, before I went on to the thiophene system, I wanted to mention to you, I've given you this nice story of how we've designed a crystal, and we looked at the stereoelectronic properties, and we saw a templated system, and we put it in benzene and got out what we expected. Well, the truth of the matter is that I had a new student working on this project, and I said to him, why don't you take cyclohexane dione and grow it from a polar solvent, and let's just see what kind of crystals you get. And so he went back in the lab and grew it out of benzene. And that's how we got those crystals. And so the story I'm telling you is after the fact, and is the rationale for why it happened. But it was another one of those things, if my student knew that benzene was nonpolar, we might not have this story to tell today. Okay, the other thing that we sometimes see happen is we grew those lovely hexagonal crystals of cyclohexane dione, and then shortly after we started getting hexagonal crystals of lots of things, and it's very unusual to see that. This is 3,5-dinitroaniline, and we think that this crystal is trilled. Now, a twinned crystal is where you have crystals growing in their normal form, and they come together at an interface, so that they're identical on either side of that interface, but they're growing in different directions. And those are called twins, and there's a twin face between these two phases of the crystal. very rarely you could get trills or higher twin patterns. We think this is a trill. We've collected some diffraction data on it, and it's absolutely confusing because what you have are 3 different crystal domains oriented in 3 different ways, and all the patterns are all overlapping one another. So we couldn't solve this crystal structure, and we've eventually solved the crystal structure of this compound by taking one of these non-twinned or non-trilled crystals. Now, along the lines of trying to design these cyclic structures, we really have put a lot of thought into what kinds of molecules can give us certain motifs. And we thought it was challenging to try and make these cyclic motifs. And so we've spent many years thinking about what molecules might really organize themselves into these cyclic motifs most easily. And recently, Tori Reese has been working on guanidinium. Here's the guanidinium sulfonate. And these crystals go together. These molecules co-crystallize very easily out of water. Is that right, Tori? Water or alcohol. And the pattern we predict is this one, where you get these double hydrogen bonded, almost like ligands. And if you satisfy all of the hydrogen bonding centers, you're necessarily going to get one of these rings. So she's grown quite a few different examples in this series. And I'll show you a packing pattern of one of them. This is with methane sulfonate. She's also made the trifluoromethane sulfonate, which has the same pattern. And down here is this 3-fold symmetric ring that we had predicted. And this whole plane looks very much like the cyclohexane dione I showed you a little while ago. It has these 6-membered rings, and they're propagating throughout the whole plane. Now, something that's very interesting about this is that there is a real 3-fold axis right here in each of these centers. But the 3-fold axis does not propagate throughout the crystal. So the crystals are monoclinic. They're not trigonal, even though each individual plane has a real 3-fold center. And what happens is that as these planes pack, they just slip, so that 3-fold axis is not in registry with the one of the next layer. All right, so you end up with a monoclinic crystal that is pseudo-trigonal, and this is what the crystals look like. They look like beautiful trigonal crystals. But we have an easy way to tell whether they're truly trigonal or not truly trigonal. And that is putting it under the cross polarizers and rotating it. And when you do that, this crystal extinguishes. So it truly does not have a 3-fold axis coming out of it, even though the morphology suggests that these are pseudo-trigonal, and the morphology is reflecting the symmetry of individual planes of molecules rather than the symmetry of the entire crystal structure. Oh, I've got to back up before I show you this one. I think this is the last example, actually. This is an example that comes from Professor Barani's laboratory. Are any of Professor Barani's students here today? So I can tell stories on him. He and I have had a joint project looking at solid-state reactivity of disulfides for some time. And many of his compounds undergo solid-state decomposition reactions where the disulfide link breaks. Okay, and then you get side products, and they recombine in different ways, and some of this happens in the solid state, and it's very interesting chemistry. Sometimes the side products decompose into gaseous byproducts. So there's all kinds of interesting phenomena that are going on. Well, this particular compound was one of our reagents, I believe, and he had it sitting in a big brown bottle, about this big, on a shelf. And we weren't working on it at that time, and it was a liquid, so this is probably about 2/3 filled with this liquid. And he just set it aside. And over a period of time, decomposition started to take place, and gases were given off. And the other product of this reaction was a solid, which crystallized. So at the bottom of the bottle, a single nucleation site is formed, and crystals start to grow. Now, I don't know why it didn't form hundreds or thousands of nucleation sites, but it didn't. One crystal started to grow. And so over time, the gas is building up. The gas pressure is building up. That's one of the byproducts. And at the bottom of the bottle, this crystal's growing. And we're talking about 3 or 4 years here. And eventually the crystal hits the edges of the bottle. But it doesn't stop growing. And the gas pressure keeps building up. And so he comes into his lab one day, and there's this horrible stench. Well, I hate to say it, but that's often the case in George's lab. But this was worse than usual. And in the corner, he sees glass and liquid that had dripped down the shelves and went over to see what he had. And the liquid had all poured out of this bottle. But what had happened is this one single crystal had grown all the way across the bottle and had pushed the side out, had pushed a piece of glass out. And that's what I'm going to show you here. Now, these are very dark. I don't know if we can turn the lights down or how we can see them better, but let's give it a try here. Here's the bottle, and there's the crystal coming out the edge, and the glass is broken all the way up to there. And now we look into the bottle, seeing this great big crystal coming out at us. And then I'm going to back up one to show you that again, because see the crystal coming out, and you even see a hint of it in the bottle. Forward, looking into the bottle, and then we took the crystal out, and it's gigantic. I mean, here's an organic biochemist growing these huge crystals, and we're down the basement struggling with our millimeter-sized crystals. But this can happen, right? And this is just an interesting phenomenon, and I'm glad he pointed out to me. And it partly goes to show that we just don't know a whole lot about organic crystals, and we often don't pay any attention. There's an awful lot of chemistry to be learned here. And at this point in time, simple visual observation is frequently going to get you a long, long way, because the phenomena have just not been investigated. No one's paid any attention to them. Well, you know, we're not the only people interested in crystals. I don't really believe that crystals have metaphysical properties. I don't wear crystal around my neck, for instance, but some people do. And despite the fact that this kind of crystallography is not my game, I'm going to show you a slide of my very favorite crystal. Crystal was grown by Kin-Shan Wang in my group, and it borders on the metaphysical. It's a diaryl urea crystal, and we believe it's an acetonitrile solvate, although we've not solved the crystal structure. The morphology in which these crystals grow is characteristic and happens every time you do it, and the entire batch of crystals looks this way. We've not just pulled one unusual crystal out of the corner. And when I see this crystal, it reminds me of this little saying that says, "Love is something, when you give it away, it keeps on coming back." And this is true in chemistry as well as in life. Okay, so I hope that you've gotten a feeling here for crystal morphology and some of the intricacies and interesting aspects of crystal growth and crystal changes, and I hope I've encouraged some of you to look at your crystals a little more carefully as you're working on them. And I'd like to thank here, I just take this one. Several people who worked on these systems. We've had a lot of people working on the cyclohexane dione systems over the years. Currently, Gandhara Ranawaki in our group is looking at lithium enolates to see if we can make lithium enolate cyclomers like the ones I showed you. Binapthal work was done quite a few years ago in collaboration with a group at the University of Illinois. The ephedrine compounds that showed the racemization by vaporization was done by Professor Grant and his group in the pharmacy department. The anthranilic acid polymorphs are being studied currently by Bill Ojala. And I'm not going to go through every one of these. I think I've mentioned most of their names as I've come to them during the talk today, but these are the students who are currently or who have recently worked on the examples that I showed you. And also in ending, I really must acknowledge Professor Doyle Britton, who's a crystallographer in our department. He has been an integral part of our work, not only in solving crystal structures for us, but in giving us inspiration and encouragement. He's a wealth of knowledge about crystals and solid-state chemistry. Several of the projects we're working on now were ideas that were generated primarily by him through discussions, and I'm just extremely grateful to him for this collaboration. And finally, I'm going to put up for people who are interested in some of the technical details, I'll leave part of this up and then I'll move the sheet. We need to have that recorded. And while that's up, I'll thank you all for attending today. Are there questions? Like I said this morning, if you ask a question, I'll repeat it so that it gets onto the audio portion. And if you don't like the question, we can edit it out. Any questions? Okay, well, thanks a lot for coming, and don't freeze on your way back over the bridge. It's really cold out there.